Barbara Cohen.
I'm Dr. Sarah Braden.
Dr. Sarah Braden, congratulations. And we're your hosts today. Just a reminder to the speakers, when you're the next speaker, please come up and get mic'd up over here and be ready to go. Speakers will have 10 minutes. We'll give you a 2-minute warning to finish up, and please be finished by 12 minutes so that we can have a couple minutes for questions.
Thank you. Sure. The first speaker will be Elise Rumpf, and she'll be presenting on the thickness of lunar lava flows, a comparison of layered Mare units with terrestrial analogs.
Great, thank you. Okay, sounds like my mic is on. So this project was inspired when all of the really great high-resolution imagery started coming in from LRO. And one of the things that really struck me about this imagery was the similarity in layered stratigraphy of presumably lava flows in the walls of Mare impact craters and layered stratigraphy of basalt flows all over Hawaii. So because of the abundance and ease of accessibility of basalt flows in Hawaii, I wanted to use them to learn a little bit about, or to assess our interpretations of Mare flow thickness estimates. So the thickness of Mare flows is important to the history of the moon and important to the history of our solar system. For one, we use lava flow thickness estimates in order to make interpretations of eruption rates, flow velocities, and the rheological properties of lava flows on the moon. And this can have implications for the emplacement of lava flows and for the volcanological and thermal history of the moon. In addition, lava flows can provide protection for ancient paleoregoliths that have become embedded with exogenous particles, including solar wind, solar flare, and galactic cosmic ray particles. They can, if they are placed on top of an ancient regolith deposit, they will protect that deposit, provided that the lava doesn't heat up the regolith completely and destroy this historical record in there. We can calculate how deep the heat pulse is going to go into a regolith deposit, destroying these records, but we have to know how thick the lava flow is in order to calculate this. So, as a quick overview, the Lunar Reconnaissance Orbiter narrow angle camera returns imagery at 0.5 meter per pixel, which is great because we're able to resolve features at about a meter scale, which includes these layered lava flows. Now, combined with some LOLA data, we're able to figure out the thickness of lava flows on the moon. Robinson and colleagues have done this at several locations in pit craters and in the walls of impact craters, and he has found thicknesses ranging from about 2 meters to 25 meters. These are on the low end, but still consistent with historical estimates of lava flow thickness on the moon. So, we looked at lava flow thicknesses in 4 craters at the lunar surface. We looked at Lichtenberg, Kepler, Bessel, and Dawes. If we move a little bit closer to look at Dawes, let's see, here's Dawes crater. In order to actually measure the thickness of these lava flows, we had to meet certain criteria in these areas. We had to have adequate L-rock coverage of sequences of laterally continuous layering, and these layers were defined by changes in tone or texture or maybe shadows, things that would indicate a change in slope or a change in material across the progression. So throughout Dawes crater, we found several areas that met this criteria, including down here in the southern region. Oh, I'm sorry for the image quality here. You might be able to see it better on the TV monitors. So we found for any of these regions that had sequences of lava flows, we picked up 2 LOLA track points to get elevation data. We connected them by a transect, and we mapped any of the layers that intersected with this transect. You can see here we have our yellow layers define certain layers, so areas where we are very certain that there were laterally continuous layers. The orange layers define more uncertain layers, so think places where maybe it's not completely laterally continuous, or this texture of tonal changes were more subtle. So to get an average flow thickness over a packet, we took the counts of the flows, both the maximum count defined by all of the flows of the certain and the uncertain layers that we found, and the minimum number of flows defined by just the certain layers. We divided that into LOLA elevation data, and this gave us an average thickness of lava flows across a transect. You see here, we Did this for 46 transects across 4 different impact craters, and we got average flow thicknesses between about 4 meters up to about 24 meters, and these are consistent with other interpretations of lava flow thicknesses using LRO data. Now we use the same techniques for terrestrial data. This is on the island of Oahu in the Hawaiian Islands. We chose to use WorldView 2 satellite data because it has the same resolution as NAC data. We visited 3 different locations across Oahu. We're here at Pu'u Kepa'ala, Pu'u Haleakala, and Makapu'u. So if we get a little closer to Pu'u Haleakala, you can see here this is the Pu'u Haleakala Ridge. We used similar criteria in order to determine lava flow thickness. We needed areas where we had adequate WorldView 2 coverage of laterally continuous layers. We also had to consider accessibility. So land ownership, if it was public or private land, if we'd actually had permission to go there. We had to consider slope. So was it steep enough that you got a clear expression of outcrops, while at the same time not being too steep that it was unsafe to climb? So if we zoom into this ridge where we did some mapping at Pu'u Haleakala, you can see here we used the same technique again, this time using USGS elevation data. We defined a transect and we mapped the flows, the visible flows in the WorldView 2 images across this transect. Now our average flow thicknesses for Oahu, we took at 8 different transects, and we found average thicknesses between about 2 meters to up to almost 8 meters. These are less than the lunar flow, or the thickness is less than we found at the lunar flows. In order to ground truth this data, we then did some field work. So here is a side view of that same ridge in Pu'u Haleakala, and if we get a little bit closer, you can see this really nice expression of outcrops in this step-like pattern. And so this is so going and measuring the thickness of these lava flows is as easy as starting out at the base of the lava flow with a measuring tape and a field assistant, and just progressively climbing up the ridge and measuring the thickness of any lava flow you encounter. One of the most significant observations we made while we were out in the field is that most of the outcrops we encountered, or not most, sorry, about half of the outcrops we encountered contained more than one lava flow. So you see here on the left, and on the left there's one outcrop about 4 meters tall, and it actually contains, let's see, there you go, oops. It contains 3 a'a flows, which are defined by these kind of recessive clinker layers in between the more dense a'a core. On the right, we have pohoihoi, some really nice developed pohoihoi lobes, and this may represent up to 3 or 4 lava flows. It might also be an inflationary feature. Pohoihoi lobes are pretty complex, and so most of the time I actually counted layers of overlapping or intercalated pohoihoi lobes as one single unit or a complex unit, because it's often hard to distinguish between individual lobes. Now, when we look at our terrestrial ground truthing data, I took the average of each flow measurement at each field site, and we found average flow thicknesses between about 1.5 meters to 3 meters. When we compare these to our satellite estimates, I'm sorry, that's a little off there. We compare these to our satellite estimates, we find that at every location, when we have a ratio of our maximum satellite estimate to our field measurement, we find that every time our maximum satellite estimate significantly overestimates the thickness of these lava flows. In 5 out of our 8 sites, the minimum satellite estimate also significantly overestimated the thickness of these lava flows. In only one location did we find that the satellite estimate underestimated the thickness of the lava flows. So we can take this to mean that in general, image interpretations are going to overestimate the thickness of lava flows in sequence. Now, the main reason for this is that because when we're looking at satellite images, what we are counting are the number of outcrops, not the number of lava flows. Our outcrop counts actually match more closely to our satellite counts than our number of flow counts. And so this means that when we are looking at satellite data, we're counting the number of outcrops, and up to half of outcrops in the field are going to have more than one outcrop or more than one lava flow, sometimes up to 5 units. This means that we are underestimating the number of flows in a sequence and thereby overestimating the thickness of individual lava flows. So what this means for the moon is that lunar outcrops may similarly contain more than one lava flow. And so this means that our measurements interpreted from remote sensing techniques are likely overestimating the Mare flow thicknesses. So when we take Mare flow thickness measurements from satellite data, we should interpret these as a maximum thickness estimate, not as an absolute thickness. These misrepresentations can, of course, lead to erroneous estimates of magma or lava rheology and emplacement, and can have other implications for the preservation of volatiles at the surface. And with that, I can take any questions. Okay.
Did you do any corrections for angles in the topographic data? So, like for instance, the Lola track versus the vertical extent of the stratigraphy in the outcrop. Did you correct for that at all, or did you just kind of estimate based on the DTMs?
Yeah, so I estimated just taking the absolute height data from the top of a transect to the bottom of a transect, and I figured if there's any slope or tilt in the stratigraphy, and if we're not making a total vertical cut in the lava flow, or perpendicular to the surface of each of the individual strata, then again, that's going to act to overestimate the lava flow, because if you're not taking a cut vertically through a section, you're going to take a cut at an angle, and it's going to end up wider than the correct vertical cut. And so, does that make sense? Okay.
What was the biggest challenge in doing the fieldwork aspect of this in Hawaii?
The biggest challenge. So the hills are covered in kiave, which is mesquite. So that was actually the biggest challenge. Is just you have to wear thick clothing so you don't get cut up by the sharp rocks and by the sharp trees, and you get very hot. Scientifically, it was fairly straightforward field work. Yep.
How similar were the instruments used for LRO versus the Earth sensing equipment for your comparative study? Were they the same exact instrument? Were there any differences?
That's a good question. I actually don't know the technical details of the two instruments in order to compare them. Yeah, we picked them based on the resolution. We figured similar resolution data would return, similar results, or at least, image interpretation or result in image interpretations that were similar. So, yeah, technically, I don't know a lot about the engineering behind the two instruments. Thank you.
Thank you for that talk. And